In this video, we'll look at answering the question, where is the particle? And I thought before we started with that, it's useful to visualize what these wave functions look like, because it's the square of these wave functions that tell us where the particle is. So we have a set of wave functions here, right? It's not just a single function, there's a set of them with different values of n. And these look essentially the same as the normal modes of a vibrating string. And so for n equals 1, for example, this wave function, if we plot it out, looks like half of a sine wave. It should be symmetric. My drawing just isn't very good. For n equals 2, we'll get one full sine wave that fits in. N equals 3, we get 1.5 sine waves, and et cetera, right? We continue on. One thing you'll notice is that for n equals 1, we get no nodes, or where the probability distribution is equal to 0. For n equals 2, we get one node. N equals 3, we get two nodes. And as we keep going up, we'll see you get an additional node as you keep going up in energy. Okay, so if we want to answer the question of where the particle is, we need to take an integral, right? Just like we talked about briefly in the video. So let's go and answer the question I asked in that other video. What's the probability of the particle being on the left-hand side of the box? Now, just kind of logically thinking and looking at this, we'd expect it to be on the left-hand side as often as it's on the right-hand side. So we should expect something a half, right? Our probability we get should be a half. That's something to think about beforehand before you even start trying to answer the question. But let's show that mathematically, according to the way we've described probability distributions, we do actually get a half. Okay, so to solve that question, what we need to do is solve this integral. So integrate from 0 to a over 2, right? That's our left-hand side of the box of the probability distribution, which is the square of the wave function. Okay, so we get the integral from 0 to a over 2 of square root of 2 over a sine pi x over a. So we've specifically picked n equals 1 for this. We could do this with any specific value of n, but we'll do it for n equals 1. Sine pi x over a times square root of 2 over a sine pi x over a dx. Okay, so we can factor out our constants here, our square root of 2 over a, so we'll get just 2 over a out front. Integral from 0 to a over 2 sine squared pi x over a. Okay, and so we looked up the sine squared integral in a previous video. You can go back and look at this or look at an integral table. But what we'll get is 2 over a times x over 2 minus 1 over 4 times pi over a times sine 2 pi x over a evaluated from 0 to a over 2. Okay, and so we can go ahead and plug this in. We get 2 over a times a over 2 minus a over 4 pi sine of 2 pi a over 2a. Those all cancel. Minus 0 over 2 minus a over 4 pi sine of 0. Just take a shortcut there. Right, and so as we showed previously, this whole term goes to 0. And if you've looked in here, highlight in a different color, the 2's canceled, the a's canceled, so we only end up with the sine of pi, and the sine of pi is also 0. So we end up with just 2 over a times a over 4. All right, our a's will cancel. That will reduce to just a 2 there. And so we end up with, as we expected, 1/2 is the answer. And so that is our probability of finding the particle on the left-hand side of the box. We did this specifically for n equals 1. We get the same value for any value of n, that the particle spends half its time on the left-hand side of the box and half its time on the right-hand side of the box. And so this jives with classical mechanics. But if we did a different slight, and I think I'll ask you to do this on your homework, maybe not, I can't remember now. But if we look at the middle of the box, we don't get something that agrees with classical mechanics. If we look at our wave function, we can see that. Right? If we square the wave function, it'll still roughly be this shape. And the particle is more likely to spend time in the middle of the box than at the edges of the box. And so that is something that's distinctly quantum, that doesn't show up if you do this problem classically.